This is the fifth lesson, the final lesson for our first unit, Geometrical Optics in PhysicsAP. And on this day, it's going to be super quick actually, we're going to take a look at what happens with a diverging mirror. These are the unhappy mirrors, right, that have negative focal lengths to them. Their focal point, their only focal point, is actually over on the dull side, so their focal length will be some negative number. And we're going to see what happens. We only need one example because every single one of them does exactly the same thing. Let's go and dive right in, and we'll see what happens to the rays here. So I'm going to draw an array. As always, I like to draw a ray that goes in parallel to the principal axis on the way in. And then I'm going to line my ruler up with the only focal point that there is in this story. It's one over on the dull side. Remember that the plan actually is that this focal point is half the distance out to the center. Right, so this is the center of the ball, and there's this big, gigantic sort of circular mirror there, and it's shining on the outside. So I'm going to line my ruler up with the focal point, and once I line my ruler up here, I can then see that, oh yeah, this ray goes like that as it bounces off. The other ray that we draw for mirrors is focal point on the way in, and then parallel out. So again, still lining up with that focal point with my ruler, I'm going to draw a ray until I get to the glass. But once it gets to the glass, that's when it's going to reflect and bounce out parallel to the principal axis. Well, this is pretty sad. There's no touching out here, right? Those rays do not actually come together. You cannot put paper out there and expect to see anything. You could still, convince some human to go and stare at this, and they will actually perceive there to be an image of the Roadrunner. Let's back calculate the rays, see if we can figure out where they will think this Roadrunner actually is. Ah, I see it. They will tell you, oh yeah, I can see the thing. It's right here. They're going to see it behind the mirror. And it looks like it's upright, and it looks like it's a little bit small. But let's just run the numbers on the math, and we'll see what the math says. So our only equation is 1 over f, for figuring out distances. 1 over f is equal to 1 over do plus 1 over di. And then we can do magnification as well. Opposite of di on top of a do. So this mirror is curved kind of the wrong way. I like to say the unhappy way. So we're going to go with a negative focal length. This one was 10, up in the top of the story there. And this story had our object 20 away, and then we'll go and look for the di. And when I tried that out, I found that the di was negative 6.67 centimeters. Checking out the magnification, I'm going to have an opposite of negative 6.67, all on top of a 20. That ends up being a positive 1/3. So what does that tell me? Well, I've got this negative distance for the image, so it's looking like we're going to have a virtual image. It does look upright. It's got a positive magnification, but it's tiny though, just 1/3 small. This is exactly the same story as a diverging lens. Always, 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 always virtual, upright, and small. Right? Creates this image that does look the right side up, but it does look tiny. You may sometimes notice that the passenger side mirror, rear view mirror on your car has this, where the things look small there. They usually have a little warning saying objects in the mirror are closer than they appear, right? Because the dump truck appears small, but it's actually really big and it's really close behind you. They do that because you get to see a little bit more of the world when you curve the mirror like that, but it does make a slightly small image. That's supposed to be the end of the story, but we've got one last little bit of space in our note package, so I just wanted to show you quickly how telescopes work. They're different, okay, so the math is slightly different than it has been for everything else so far, but it ends up being some pretty simple math, so I thought I'd show you quick. The idea of a telescope is you put two lenses together with different focal lengths. This first one's going to be a 30, and the next one's going to be a 5. And then you arrange them so that they have a common focal point. So here you'd have to make this distance 30, and then you'd have your focal point right here. Whoa, that's a bit of a mess. and then a 5. So you'd have to create some sort of like telescope tube that you could put this all in, where this was 35 centimeters long. Now the ray diagram is a little different, right? It's not quite the same story, but it's close. If you had rays come from some galaxy far away, sounds like Star Wars, if they came in parallel, when they got to this lens, they would then go through its focal point. But keep on drawing it. Once it goes through that focal point, hey, that's the focal point for the next lens. So we just drew a ray that was focal point on the first side for lens number 2. It's going to come out parallel. Same thing with a ray maybe down here on the bottom side of this galaxy. Comes in parallel, it bends. It's going to go through the focal point of that first lens, but that's the focal point for the next lens. So once it gets to here, it comes out parallel. Is it real or is it virtual? I'm not even going to answer that question. The only one I'm going to put on here is it is inverted. You can kind of see from the blue and the green rays that it does get flipped around. So don't really worry about whether it's real or virtual. Turns out you could put paper out here and you would actually see it. So maybe it's real, but you'll look back with your eye and you see it out here. Maybe it's virtual. Let's not worry about that. And for size, instead of worrying about whether it's like big or small, usually we just want it to be bright. But astronomers do also like to calculate what we call the angular magnification. It's different than every magnification we've done so far. The angular magnification for a telescope is actually, it's so simple. It's just the ratio of the focal lengths. So in this particular story, it would be a 30 divided by a 5, and it would be a 6. So we would say, oh yeah, things are 6 times as big in the telescope. More important than things being 6 times bigger, they're going to be brighter because you're going to be capturing so much area when you funnel it down into your eye. And that's one of the key things with telescopes, is just not making things so large, but just making them bright enough for you to see. Doesn't really fit in with the PhysicsAP curriculum, but had a little space there on the note package, and I just wanted to show you how telescopes work. It's really just a couple of lenses. Sometimes use a mirror for the first one, but a couple of elements, and they have different focal lengths, and with that you can get some magnification. And that wraps up our unit on geometrical optics.